Hi, welcome to the second part of the lecture on trees and forests. So we have discussed how we can use trees to classify cases or also work it as a regression model where we have a set of variables and we want to group cases using decision trees by every time splitting the sample based on some value on one of the variables. So for example, we can first split on whether it's a rich or a poor country, and then second for rich countries, we might select on whether it's an oil state or not, and for poor countries, we might select whether it's a conflict-prone country or not, and then when we have a conflict-prone poorer country, then maybe with higher ethnic fractionalization, we might have a higher probability of being a democracy or lower, etc. So we can classify based on a set of variables every time splitting the sample based on the value of one of those variables. But there are some problems with this method. So the method can be quite sensitive to small changes in the data. It can be easily overfit to one particular sample. Or another problem that I had not really discussed in the slides is that for some cases, some variables will have a lot of variation between observations, and other variables will have very little variation between observations. And random trees tends to zoom in on those variables with high levels of variation, regardless of whether it is an important variable for the classification. So it selects the variables most likely to help you separate one category from another. But if the variable has a very high level of variance, it's more likely to be selected, even if it's maybe not the best variable to make the selection. And people have come up with methods to try to address this. And one way to do that is to take a lot of trees together. So instead of looking at one regression tree, we do many regression trees or classification trees. And then we need to somehow aggregate again. And so we get the forest. Yeah? So let me continue the lecture by talking a little bit about random forests and similar kinds of methods that turn singular modules into many modules. So we are going to talk about something called random forests, which is basically a tree model replicated many times and then averaged. But the same idea, the idea of using one classification model many times and then come up with some kind of average, is actually a more generic idea. It can also be used with other models. So let me switch to the slides. So we already talked about the trees, and we continue with the forests. So trees and many other methods can be sensitive to specific outliers and particular data sets, and it quite easily overfits. It zooms in very precisely on the data set that you have and then becomes less good at predicting outside the data. And it also has a tendency to focus too much on particular variables and undervaluing other variables. Now, one thing we can do if we have problems with this small variations in the data set leading to big changes in the predictions, we can try to take different samples of the data set, take different chunks of it, estimate separate models, for example, 3 models on each of them, and then collate them all together. In machine learning, this is called ensemble learning. And ensemble learning, the idea is that if we have many classifiers, or for example, the same model on many slight variations of the data set, or many slight variations on the model itself, and we keep repeating them, and we then take an average prediction, we will overall do quite well. The mathematical proof suggests that as long as each of these estimators is better than throwing a dice, then many of them together will give a much better prediction than any of one of them separately. The same idea actually works with wisdom of the crowd. So people are in a way estimators, can be used as estimators. I can show you a jar with a lot of candies and ask you how many candies are in there, and that is an estimator. And we know that your estimate is likely to be wrong, right? We don't really know how many candies are in this jar. But if I ask many people, for example, in a large lecture theater, and I ask everybody to make a guess, and we then take the average of all those guesses, we probably have quite a good estimate of the number of candies in the jar. And this is because each of those guesses is likely to be wrong, but they're always a little bit better than just picking some random number, because you can make some kind of guess. So the guess is crude, it's rough, you're likely to be quite far off, but some people are going to be far off by overestimating, some people are going to be far off by underestimating, and on average, you will actually get quite a good estimate. And that is the idea of ensemble learning. So the wisdom of the crowd is the same idea applied to people that ensemble learning is applied to statistical models. So we are going to do this. We're going to generate many variations of the data set and then keep running the same tree model and then keep estimating. Now, the main idea that we will use here to generate this data set is a little bit complicated, and I don't want you to worry about it too much. But just to let you know what the idea is. The idea is called the Bootstrap. And a Bootstrap sample is a very specifically defined sample. It is a random sample of the original data with the same size, so they are exactly the same number of observations as in the original data, but they are sampled with replacements. So imagine I have 20 observations and I pick randomly one of those observations. Maybe I take the 5th one. And then I put it back in the sample and I take another random observation, maybe this time the 8th one. I put it back in the sample and I take another random observation. Maybe by chance I pick up 5 again. Now I have the 5th observation, the 8th observation, and the 5th observation. So I have a data set of 3 observations, but there will be some duplicates. I might do this 20 times, and the result will be I have a new data set of 20 observations, just like my original data set of 20 observations. But while in the original data set, each observation occurred only once, in the new data set, each observation might occur multiple times. Below you see it lined out with an example data set. We have a data set that has an observation 1, 2, 3, 4, up to 12. And then we take different Bootstrap samples, and each time it is a random sample of those 12, but with replacements, so with duplicates. Right? Sample 1 had 4 times the 7, 2 times the 12, and then the 3, the 4, the 5, and the 6, and the 10. Sample 2 has 2 times the 5, 3 times the 7, 2 times the 3, etc. Yeah? So these are random samples of the original data set. They have the same size. They're always just 12 observations. But they are nevertheless each time a little bit different because some observations are duplicated and some observations are left out. And we can do this many times. So the trick here is that we take many of these samples, always a random selection of the original data set, always of the same total number of observations, always with some duplicates or triplicates or quadruples, etc. Always with some left out. So each time the data set is similar to the original, but not quite the same. And each time we run the same tree model, and we get the same kind of classification, we get a prediction, etc. But now, if the model is sensitive to small variations in the data, we will get different estimates on each of these samples because these different aspects they vary each time. So we can, for example, use this model to predict for observation 1 whether it's a democracy or not, and for observation 2 whether it's a democracy or not, and for observation 3 whether it's a democracy or not. And then, because for each sample we get a different regression tree or classification tree, we can't simply plot that tree, but we can look at the average prediction for 1. So we can say that in 90% of the trees, across 90% of these Bootstrap samples, we find that observation 1 is a democracy, and in 10% we find it's not. Then our prediction for observation 1 is 0.9, and so forth. So we can take an average of the prediction. We can't really take the average of, we can't draw a regression tree for the entire sample. So that's a Bootstrap sample. Don't worry about it too much, but it's quite an interesting concept. It's the idea of sampling a new data set over and over and over again from the original data set with the exact same number of observations, which is done by sampling with replacement, which means that some observations will be duplicated and others left out. Now, there are different ways of then using ensemble techniques on classification trees. And we are going to focus on random forest, but I just want to let you know that there are multiple ways. In data science, they will often talk about bagging. Bagging means that you take Bootstrap samples, so we take many samples of the same size, randomly selected with replacements. We estimate trees, but we never prune them, so it's always the full tree. And then every time we use that tree to predict for each observation what the classification is, and then we classify on the basis of majority votes. A random forest also takes Bootstrap samples, and for each sample estimates a tree without pruning, and we average across. But the big difference now between random forest and bagging is that it will not only select a random set of observations, it will also every time drop a few of the variables from the model. So this addresses really this problem that I mentioned, that some variables, because they have a large amount of variation, even though they're not too important for the classification, they might still be selected very often by the regression tree model because of that large variation. Using Bootstrap, using random forests means that we not only randomly select these samples so that we have many samples and we are less sensitive to variations in that sample, peculiarities in these samples. We also randomly select a subset of the variables each time so that we can estimate different models, where maybe that variable with high variance that is not so important is occasionally left out. And then we get very different trees and very different predictions. And finally, there is boosting. Boosting is not really based on this bootstrapping idea. Here you estimate a small tree with very few branches, highly pruned. We use that to predict, and then we look at the residuals. We look at all the misclassified observations, and then we estimate a model just on those missed observations to keep improving. So this one focuses first on a very crude model, very crude prediction, then looks at the misclassifications, and then reruns the model over and over until we have everything classified. A little bit of a different idea, but also again, a wide series of tree models that are performed in sequence to then come up with a result. So the implementation in R is relatively straightforward. So we open the library random forest. We can save the random forest. We have a dependent variable y. We have independent variables x1 and x2. We can save the output of this estimation under any name, for example, t. We can use the predict function to get a classification for each observation. And we can create a confusion table by comparing the prediction with the original labeling. We're still in supervised modeling here, just like with trees. So we know what y is, we know the correct classification, and we compare the prediction from the model with the correct classification. So these first 3 lines of code, they are pretty much like how we do trees. But there's an important line missing here. This is the plot command, right? Because where for the tree, we can come up with a nice plot that shows you the classification tree, that shows you all the decision steps. With random forest, we have many trees, and there's no way of easily visualizing or interpreting that. And there's also no average tree we can draw. There's no way we can do that. So unfortunately, we can only resort to something that is a little bit less informative, which is the importance of each variable. It shows you each variable in the model and how important it was on average to predict the outcome. Yeah, so variable x1 has a Gini coefficient of 17, x2 has a Gini coefficient of 22. This means that x2 was a little bit more important than x1 to estimate what the outcome is. But it's not so surprising. In our sample data, as you may recall, we had this horizontal line where above the line in x2, only non-democracies, 60% or 70% of the data. Below the line, half or so democracies, half not. So if you already know that you're above or below this line on x2, then you have a pretty good prediction. If you only know where you are on x1 and not on x2, you have a much poorer classification. So we could see in the graph that x2 was a bit more important than x1 to predict whether it's a democracy or not. So in random forest, we can just make a table like this. It shows you for each variable how important it is. We can come up with a prediction that is probably a better prediction. A prediction that is, we can see in the confusion table here, that the prediction is pretty good. We can come up with a predictive model that is probably better if we have new data coming in. say you have new observations on x1 and x2 and you want to predict y, this model is going to do better than the tree model. But there's no easy visualization. There's not so an easy interpretation other than this variable was more important than that variable to explain the outcome. So that's where we focus. On bagging and boosting, I want to say a little bit less. This is really sort of an additional technical topic. The random forest is the important one. Right, so bagging was similar to random forest, except we just selected these bootstrap samples. We didn't also select variables. So in the random forest command, there is the mtry parameter, and the mtry parameter is the number of variables to include in each tree. It will normally come up with its own ideal default value. If you want to force it to always include every variable, you just have to put the number of independent variables you have there. We have x1 and x2, we have 2 independent variables. So we set mtry to 2, and that forces the random forest to always include every variable. And if you include always every variable, then we are back. We can go back to this overview we had here. The only difference between bagging and random forest here is that the random forest randomly selects a subset of the variables. The bagging does not and takes all the variables. If we set the random forest to always randomly select all variables, we are basically using bagging. So bagging is straightforwardly implemented and exactly like random forest. Boosting is a bit more involved, requires a different kind of package, a bit more coding. It's also the prediction does not automatically predict a response like it did with random forest. It all comes a little bit more complicated. I don't really want you to worry about this. Here's the sample code for this particular example to perform boosting if you want to, but don't worry about these details. So, so that shows you a little bit how to use random forests and how we can look at importance rather than showing you regression trees. And in the lab, you will see some examples of this. And you can also plot the importance to visualize what are the important variables and not. That's all displayed in the lab, and we can also discuss in the live class session. Okay, thank you for listening.